Howdy. All right, here we go. 16.2, electric potential of a point charge. All right, so if you remember, 16.1 was all about the concept of electric potential, and it's sort of the ability to do work because of an electric charge. It is measured in volts, if you remember this. Yes, I hope. Okay, I'm moving myself to the bottom here. Woo. Okay. So now instead of talking about parallel plates, because we were talking about two parallel plates where we were putting a test charge in the middle and then being able to calculate what was going on, and I just cannot get used to the camera being straight in front of me. I'm like looking at myself and it's not working. It's all good. Okay, so there's your Mrs. Kelsey moment for the day. All right, so here we go. So now I have a point charge by itself in the world, in the universe, not in between parallel plates, okay? It's taken, so if you think, and if you remember the first Walter Lewin video that we watched together, he sort of talked about this. So the electric potential, if he put the charge in his pocket and if it was out in the lobby and all that other good stuff that he was talking about. So the point of a zero potential around a charge is infinitely far away from the charge. So again, this is an action at a distance sort of situation where the field will go on for infinity, just get very, very small. Okay, so the potential that is created by a point charge called Q at any distance r from the charge is this. So this is the electric potential generated by a charge. And if you notice, this is Coulomb's constant. And let me type, here we go. Oh my gosh, change the font color. I don't know. I'm thinking, I guess go with red. Okay, so K is 9 times 10. I don't know if I could do this. Shift plus 9. Nope. 9 times 10. Here, let's do it this way. E 9 times 10 to the 9th. How about that? Coulomb's constant, okay? Q would be the charge on your object, or the charge on your charge. Charge of point charge. And R is your distance in meters. And I can't spell. It's all good. All right, so there you go. Better than my horrible handwriting? I think so. All right, so then we got to move back to the pointer, change slides. All right, so now we're looking at electric field and electric potential. Obviously, they depend on distance, okay? If you notice the formula for electric field, and that, again, if you remember, is capital E is field, right? It's a 1 over r squared relationship, so it falls off faster. Okay, we're all about logarithmic relationships right now. And electric potential is V, and it's a 1 over r relationship, so it doesn't fall off quite so quickly. So far, so good? So far, so good. Okay, so then if I have multiple point charges, just like Coulomb's law and Coulombic love triangles and all of that other stuff, we're again using superposition, so it's the algebraic sum of all of the charges. Remember, this isn't a vector, so it's much better and much easier. It's just the algebraic sum of all of the potentials of all of the different charges at that point. Okay, so it's somewhat a lot easier. Okay, I like this diagram a lot because it gives you a visual situation. Okay, so this is a electric potential of 2 point charges. Okay, this charge is positive, and the way I knew that is because the potential is positive. This charge here is negative, and I knew that because it was going down. So if you think about 2 point charges in the middle of these two spots, okay, along this axis, what's going to happen is if I get a positive charge, if I get a test charge near this, it's going to be sucked up into this well of potential. Or if I bring a positive charge in here, it's going to be sucked down into that well, okay? they're doing work. The potential is doing work on the charge, okay? And I like that a lot. It helps you visualize that whole potential idea, or a potential well, okay? If you're working with circuit boards, you're overcoming those potential wells with zeros and ones, and those potential wells are how we store data, okay? So here's an example, and they're very, very simple. You're just using that potential equation, okay? So here's my point charge. I am this far away. The potential at point P is equal to that, okay? If I have two charges, I can then calculate the potential energy. That should look familiar to you, okay? The work is equal to the potential energy, which is equal to there, which is also equal to that. So this should go on your card, okay? Please make sure this goes on your happy slappy card. Oh God, I did this really badly. Let's try that again. Backspace, delete, undo. This should definitely go on your card along with those other equations we've been talking about, okay? Pretty straightforward. It's not so bad. Do some problems so that we can go over them together. We can even do a meet. I don't mind, okay? If the charges have the same sign, the potential energy is positive. Makes sense, right? I have to do work to move things, to move them, okay? If they have opposite charges, the PE is negative and it's doing work. It's giving you work to the system. Makes sense? So far, so good. Here is your really long and drawn out thing. Draw a diagram, calculate the distance in meters, use your potential equation, which again, this should definitely be on your card if you didn't already add it to your card before, okay? Make sure you include the sign here because these are all scalar quantities. So you don't have to think about direction anymore. It handles it for you. It's a beautiful thing. Okay, use the superposition rule. When you have multiple charges, you're taking the algebraic sum. So again, if you keep the charge, the sign of the charge, it will all work it out. Potential is a scalar quantity. Yay! No more vectors. So you don't have to break it into its components. You just add each one at that point. Okay? And then I believe we are talking very briefly about 16.3, which is just talking about potentials and conductors, okay? So they're giving you some ideas here, okay? And we sort of touched about this before. All points on the surface of the conductor have the same potential. And then as you move out from the conductor, that potential gets less, okay? Inside the substance, there is no potential, okay? Because there's no electric field. And then we will pick up that in the very next video. Let me type out the questions that go, the essential questions that go with this. So 16.3 problems. Okay, they are on page, where am I? Page 594 of your textbook, and they are numbers 11 through 13. Okay, and I will be more than happy to jump on and do those with you. I'm going to go get my document camera at school tomorrow, so I can actually do them by hand with you. Whatever we need to do, we're going to do it. Okay. Miss you guys a lot.